Electricity service is one of the founding pillars of modern society. It powers everything, everywhere. To operate the electric grid reliably and safely, power utilities have deployed various grid applications, including teleprotection, SCADA, operational voice, and CCTV. As these applications and their associated subsystems are deployed throughout the infrastructure, in substations, operations centers, as well as data centers, utilities need to provision segregated virtual private networks, or VPNs, to interconnect them. Let's look at some comparisons between conventional network management techniques and the use of the NSP for VPN provisioning. In a typical critical infrastructure, there are hundreds, if not thousands, of remote sites. Each site will have a gateway router connected to individual application subsystems and devices. Provisioning all of these devices and the transport infrastructure with a conventional network management system, or CLI, becomes a labor-intensive and error-prone task, with many touch points at the edge and in the core of the transport network. In addition, after any application upgrade, changes such as increasing bandwidth may be required. Making global changes requires a lot of manual effort, potentially disrupting operations. The NSP greatly simplifies this process, resulting in error-free, scalable, and secure operations. Templates based on standard configurations, reflecting network and service policy, are used to provision the network. The NSP auto-configures the multi-vendor, multi-layer network infrastructure. The end-to-end service is configured, and NSP also discovers and allocates resources at every layer to support this service. This can include service tunnels, label-switched paths, and physical media. The NSP automatically and intelligently establishes the optimal path for efficient, reliable communications. A teleprotection system typically has two protective relays connected to the network. These relays exchange real-time power circuit information in a TDM format, requiring a circuit emulation service, or C-line. Teleprotection requires stringent QoS, that is, quality of service, to ensure low delay and jitter. The form of teleprotection called current differential protection is required in the most demanding power grid applications. Differential protection requires not only low delay and jitter, but also low delay asymmetry, that is, the difference between the forward path and reverse path delays. Additionally, being a critical application, teleprotection traffic also needs to be protected from cyber threats. In this video, we will now take a look at using the Nokia Network Services Platform, NSP, to provision a VPN service for teleprotection. And also, we will use NSP analytical tools to monitor its correct operation. Utilities can quickly and easily provision a C-line service to transport differential protection traffic by using the service fulfillment application from the NSP Launchpad, without extensive network expertise. This is the menu for existing services. From here, you can create a new service for differential protection. When creating a new service, you can simply use a predefined template for differential protection. The service name is Relay Dublin. The service template has defined that a tunnel profile called Differential Relay Services Tunnels, engineered to support differential protection, will be used. Let's take a look at what is defined by this tunnel profile. This profile specifies a new tunnel to be created by the RSVP protocol using a strict deterministic path with bandwidth reserved in the network. A check is made to ensure that connectivity between the endpoints is possible. The protection type, unprotected or protected, is also checked. To meet the delay symmetry requirement, you can also enforce the bidirectional tunnel pair to be symmetrical in the forward and reverse directions, making sure the network delay is symmetrical in both directions. Furthermore, to meet delay budget of differential protection, you can also request the tunnel to have a delay target to meet a certain value, 5,000 microseconds or 5 milliseconds in this case. The virtual circuit type, or VC type, would be CES over PSN. Additional parameters are the jitter buffer depth and the payload size. Asymmetrical delay control, or ADC, can be enabled to tackle delay asymmetry in the jitter buffer. To protect the service from cyber threats, Network Group Encryption, or NGE, can also be enabled. Now we're going to create endpoints for this service, making use of certain interfaces in the network. We will call them Dublin East and Dublin West. We will pick a time slot for each endpoint, time slot 20 on both ends. After these are selected, the service is ready to be deployed. Just click the Deploy button. Or you can save the service and let another colleague deploy it when needed. Once the Deploy button is clicked, the service goes into the deploying phase. The NSP will communicate with the routers to check for resources and connectivity, and download configurations, creating the tunnels based on the tunnel profile requirements for latency and strict path symmetric in this example. You can now see all the parameters of the service. You can see the topology view of the service between the two endpoints in Dublin East and Dublin West locations. You can also see the two unidirectional tunnels in the forward and reverse directions. You can examine the network details and status of each tunnel. For east to west tunnel, the network delay, excluding the packetization and jitter buffer delays, is 70 microseconds. For the west to east tunnel, the same network delay is achieved. Both tunnels traverse the same route in opposite directions. You can also view the service at the physical layer to discover which network equipment, interfaces, and links the service traverses. After the C-line is live, carrying differential protection traffic, you will want to proactively monitor the service. You can use the NSP Analytics application to monitor the health of the C-line service, particularly the jitter buffer depth and asymmetry. After you have created the service, we can use NSP analytical tools to verify its correct operation. NSP Analytics provides reporting on utilization, uptime, and even jitter buffer conditions. This graph shows jitter buffer depth in microseconds at endpoint 1 and endpoint 2 of the C-line service. As attaining delay symmetry is a quality of service requirement, you can also view the jitter buffer asymmetry history to ensure the C-line continues to meet the delay symmetry budget. In this graph, you can see that the jitter buffer asymmetry has been mostly kept well under 500 microseconds, or 0.5 milliseconds. The worst measurement, captured on April 29th, 10 a.m., approaches 750 microseconds. Therefore, you can rest assured that the C-line service is working well for differential protection. With NSP, service provisioning and fulfillment is error-free, reliable, simple, intuitive, and efficient. The NSP capabilities are at the leading edge in communications network management, optimization, and automation. The NSP supports the rapid isolation and resolution of network and service performance issues. Root cause analysis can reveal the underlying causes. With these analytical tools, you can closely monitor the service performance and proactively remedy any degradation, ensuring the differential protection application works flawlessly 24/7.